Alright, welcome to today's lesson. In today's lesson, we're going to talk about set theory. So we'll be going deep into sets. So if you are in Delsu, your set is in your MTH 101. And if you're in UNIBEN, your set is in your MTH 110. So basically, all 100 level students, probably engineering and some other faculties, they will still treat this topic, but it's the same thing we are going to do. So it depends on your course code. So let's just start up sets. So, but before we start, please do not forget to like and subscribe to this channel. So, sets are a collection of objects. In some textbook, you will see that sets are a collection of well-defined objects. But I do not agree with that definition, because any object at all is a set. You can just say it as a set. But you not define, you not explain and say, okay, this set is well-defined and this set is not well-defined. So I think the best explanation to give is that set is a collection of objects. That's the best explanation, not just well-defined objects. Because we have singleton sets where there are nothing inside the set. We say it is not well-defined. So sets are a collection of objects. Now these objects are actually the elements of the set. They are the children of the set. They are the elements of this set. So when we talk about sets, we'll talk about some objects. These objects are what we call the elements of the set. Now, for us, if there's a rule that makes an element belong to a set, we say the set is well defined. This is where the well defined comes into place. Now, if we can define a set, and if there's a rule that says that this element belongs to this set, we say that set is well defined. Let's say, for example, let A be the set of all 100 level students in Delsu. Now, it's easy to know all 100 level students in Delsu. So we say that this set is defined. It is properly defined. But imagine we say let A be a 19-year-old student, a 19 years old student in 100 level now, but born in 1665. Look at this. Is this even possible? We have a 19-year-old student now in 2022 and is a student of maybe UNIBEN, and we are told that that 19 years old student was born in 1665. There's no student like that in UNIBEN now. Please, if you have, you can let me know via this comment section. So because we cannot actually define this, we say this set is not properly defined. It is not well defined. So basically the elements of this set is zero. Like there's no element here, not just zero, there's no element here. So quickly, there are two ways of writing sets. Two ways we denote sets. The first one is the roster method, and the second one is the rule method. The first one is the roster method and the second one is the rule method. Now, suppose you have a set, let's say A. First of all, the first thing you must notice is that the set is written in capital letter, while this object, the elements inside this set, are in bracket. They are enclosed in brackets and they are written as small letter. Now, when you list these elements in this set, when you list out this element, no matter how many they are, if you list these elements out, it is the roster method of writing that set. Let's say A is the set of all even numbers. Even numbers include 2, 4, 6, 8, ... So because I listed out these elements, the method at which I wrote the set A is what we call the roster method. But if I want to use the rule method, I'm not going to list these elements out. I will just use a statement, a mathematical statement, to say that these are even numbers. So instead of me listing these elements out, I can as well say, let A be the set of all x such that x are even numbers. Even numbers. This is where I'm closing the bracket. So anytime you see this stroke, sometimes you see it as x dot dot. What it means is that such that. So if you are reading this is what we call the rule method, because you are not listing the elements out. You are actually using a mathematical statement to define these elements. Now it is read as A is a set of all x, then this stroke means such that. So we say A is a set of all x such that x is even, or x are even numbers. So if you are reading this, for example, so this is read that A is a set of all x such that x is a student in delta state. So if you arrange your set problem like this, it is called the rule method, because you did not list out the elements. But when you start listing out this element, instead of you writing it like this, you want to start listing out this element. You could say no need for this dot dot. You could say Obiora, you are the one watching this video now. We have Chioma, you are there watching this video. We have Chibuzo, you are there watching this video. Then you outside the country learning sets. George, you are there watching the video. George, you know, nice names, not like these Igbo names here that are not really nice. We have George and other names. So because I listed these students that are in delta states, there are so many students. This becomes the roster method. But when I just use the mathematical statement to list them out, instead of me listing them out, it is called the rule method. So quickly, let's talk about some terms used in set. Some terms that are usually used every day in set. So there are basically 14 terms we are going to talk about. After these 14 terms, we'll talk about number system, so you understand numbers. So the first one is the universal set. So the first one is the universal set. Let me call it 1, the universal set. Now, I usually say universal set is like in charge of every other set. Now, universal set is actually a set that has different subsets. Now, when I use the word set, it means that there is elements. But when I use the word universal set, it means that they have subsets, smaller sets, that these sets actually have their own elements. It is possible that these subsets still have other subsets. Let me use, for example, take for example Africa. Let's say Africa was a universal set. Africa has so many countries. Now these countries have elements. These elements are we, the humans, living in it. Now these countries are actually the subset of Africa. Or let's take Nigeria for example. If Nigeria was a set, a universal set, now Nigeria has 36 states. These 36 states are actually the subset of Nigeria. So we, the elements of these states, are actually under the subset. Like right now, I'm teaching from Edo State. I'm a subset of Edo State. Whilst Edo State is a subset of Nigeria. While Nigeria is a subset of Africa. And Africa is probably a subset of the, let me say Earth. And Earth is a subset of the universe. And the universe is a subset of, let's say, God or one thing or the other. So that's how it works. So the universal set actually is the father of every other subset. Now, let's talk about subsets. Now let's consider two sets, A and B. A and B. Suppose that A has these elements 1, 2, 3, 4. And B has these elements 2, 3, 4. Now because every element in B is also in A, but there is at least one element in A that is not here, which is 1. We can say that this B is a subset of A. Because everything in B is inside this A, but there are some things that are in A that are not in B. We can say that B is a subset of A. So sometimes we can use subset interchangeably, even if we're not talking about universal sets. We can say this is a subset of A. Let's say we have another set C. 1, 2, 3, 4, 5. We can say even when B is a subset of A, that A is also a subset of B, because everything in A is inside B. But there's something in B that is not inside. There's something in C that is not inside A. So this is a subset of this, while this is also a subset of C. So that's for subset. Let's talk about complement set. let's talk about complement set. Now, when we talk about complement sets, first of all, I forgot, for subset, anytime you see this is the symbol they use for subset, what they mean is A is inside B. That's the best way of explaining it. So A is a subset of B. So this is read as is a subset of. So A is a subset of B. If I decide to change it to this direction, this means B is a subset of A, meaning that B is inside A. But anytime you see this, it means that even as A is a subset of B, but everything in A are in B, everything in B are in A, there's no difference between these two. It means that these two sets are equal and are subsets of each other. Let's say if A was 1, 2, 3 and B was 2, 1, 3, they have the same elements. So because they have the same elements, we say A is inside B but is still equal to B. So that's the notation we use to represent subsets. So let's talk about complement sets. When we talk about complement sets, we always relate it to the universal sets. So nobody will ever ask you about complement sets if there is no universal set. So complement set is with respect to the universal set, set complement. Now let's say we have a universal set. The universal set is usually denoted as U. That's the symbol they use to represent universal set. Let's say the universal set is 1, 2, 3, 4, 5. And let's say A is 1, 3, 5. And let's say B is 2, 4. Now, whenever you see complement, it is written as, the complement of A is written as A prime. You see a small one at the top. It's written as A prime. It means that you should list out the elements that are in the universal set but are not in A. So whenever you see A prime, it means list out the elements that are in the universal set but are not in this set A. Those elements include 2 and 4. But for B prime, the same thing. List out the elements that are in the universal set but are not in B. Those elements include 1, 3, 5. That's how complement set works. It's like listing out the elements that are in the universal set but not in the particular set you are working with. So the complement of a set C, for example, are those elements in the universal set that are not in the set C. That's for complement set. Now let's talk about some types of sets you easily see. Let's talk about the finite set, or finite as some people pronounce it, the finite set and the infinite set. Now when we say something is finite, it means that it has ending. You know the beginning and you know the ending. But when you say something is infinite, it means it's either you don't know where it started from, or you do not know where it's going to end, or you don't even know where it started from and you don't know where it's going to end. So let's say A is the set of all numbers. Don't forget this notation. A is a set of all x such that x is all numbers. And let's say B, for example, is 1, 2, 3, 4. Now, because I know the starting of these numbers, it started at 1 and it's going to end at 4, and I know the numbers here, I will call this a finite set. But for this, the question is, how do you know all numbers? If you want to list all numbers, you will list 1, 2, 3, 4, 5, 6, 7, 8 till you are tired. You will never get the ending. So it is impossible to list all numbers. So this set here is actually infinite because we do not know how many elements are there. Now, the fifth one is actually the number of elements here. The sixth one, sorry. Now, the number of elements in a set is what we call the cardinality of the set. The number of elements in a set is what we call the cardinality of the set. So this set has 4 elements. So it means that the cardinality of this set B is 4. Now, whenever you do not know the cardinality of a set, because it is too much, probably the cardinality of that set is infinity, we call that set infinite set. So the cardinality of this set is infinity because we do not know how many elements are inside this set. So it is an infinite set. And this one is finite because it has 4 elements. So the cardinality of a set B, for example, is written as NB. So anytime you see this NB, it means how many elements are in this set. How many elements are here? 4. Let's say you have a set A as AB 1, 3. Now, if you see NA, what it means is what is the cardinality of A, meaning how many elements are in A. There are 4 elements here. So whenever you know the number of elements of a set, it is finite. If you don't know the cardinality, it is infinite. So let's talk about the 7th term used in set. The 7th term used in set. We have equal set. And 8, we have equivalent set. Now these 2 sets are really confusing. This is where problem comes in. These 2 sets are really confusing. Our students confuse themselves with this. Now 2 sets are said to be equal if they have exactly the same elements. If they have exactly the same elements. But for you to know an equivalent set, they must have the same number of elements. So 2 sets are equal if they have the same elements. But 2 sets are equivalent if they have the same number of elements, meaning they have the same cardinality. So let's consider 2 sets. Let's say A, 1, 2, 3, 4. B, 3, 2, 1, 4, 3. Although I repeated this, then C, precious, peace, gift, joy. Now, these 2 sets have the same elements. This one has 1, 1, 2, 2, 3, 3, 4, 4. But although this one has 5 elements, now because these 2 sets have the same elements, we are not talking about the number of elements now. Because they have the same elements, we say they are equal. But these two sets have different cardinality. The cardinality of this one is 4 because there are 4 elements here. The cardinality of this one is 5 because there are 5 elements here. So it means that if these 2 sets are not equivalent, we said for 2 sets to be equivalent, they must have the same number of elements. But these 2 sets are equal because they have the same elements. Now let's consider A and C. The cardinality of A is 4. The cardinality of C is 4. So because they have the same number of elements, we say A and C are equivalent, but A and B are equal. That's for equal and equivalent sets. Now let's talk about the 9th one. Singleton Sets. Singleton Sets. As the name implies, single, straightforward. Any set that has only one element is called a singleton set. So the cardinality of a singleton set is actually 1 because it has only one element. So let's say we have set 1, 2, B, we have 1, C, we have 0, and D, we have this. Now, there are 2, this one, what this means is there is nothing inside here. This C has an element. The element in this set C, is 0. So don't make the mistake of saying because it is 0, it does not have any element. It has an element, but the element is 0. So it has one element. This one has one element. This one has 2 elements. So the cardinality here is 2. The cardinality here is 1. The cardinality here is also 1 because it has one element. But this one, there's nothing inside here. There's no element inside here. So the cardinality of D, sorry for using a small letter, the cardinality of D is 0. There's no element. So whenever the cardinality of a set is 1, it is singleton set. But whenever the cardinality of a set is 0, it is called a null or empty set. So because this one has nothing inside it, This one has something. What it has is 0. But this one, because this one has nothing inside it, we call this a null set or an empty set. So sometimes if you don't see an empty set like this, they usually write it as phi. This is the symbol they use to represent empty set. So that's for singleton and empty set. So let's quickly come back. If you know the cardinality of a set is the number of elements in the set. Now when you know the number of elements in the set, it is finite. When you do not know the number of elements in the set, it is infinite. When two sets have the same elements, they are equal. When they have the same number of elements, the same cardinality, they are equivalent. When the cardinality is 1, it is singleton. When the cardinality is 0, it is null or empty set. So that's for the first one. So let's talk about the 11th one. Let's talk about the disjoint set. Disjoint set. Now, two sets are said to be disjoint when they have nothing in common. Okay, let's just use this as an example. Now, this set and this set have something in common. They have an element in common. This element they have in common is 1. So, because they have an element in common, they can't be disjoint. Because we said disjoint sets two sets are said to be disjoint if they have nothing in common. This one and this one, they have something in common. But A and C do not have anything in common. There's no 0 here, there's no 1 here, there's no 2 here. So because A and C have nothing in common, they are said to be disjoint sets. Now what if they have something in common? When two sets have something in common, they are said to be overlapping. They are said to be overlapping sets. Or in some textbook, you see it as non-disjoint sets. Non-disjoint sets. When we talk about Venn diagrams, I'll be explaining some of these disjoint and non-disjoint sets. Some of them for you. Now, if they have something in common, A and B have something in common, which is 1 and 1. So because they have 1 in common, they are overlapping. But A and C have nothing in common, so they are disjoint sets. Let's say we have 2, 4, 6. And we have, now if you observe, C and A has something in common, which is the element 2. So they are overlapping sets. But C and B has nothing in common, so they are disjoint sets. So that's for disjoint and overlapping sets. Now let's talk about the power set. The power set. The power set. Power set is quite confusing, very, very confusing, but it's easy. Now, whenever you have a subset, let me use a subset, or let me say a set. Whenever you have a set, let's say you have P, Q, R as the elements. Now, this set can form several subsets. This set A can form several subsets. So the possible subset that this A can form is P. It can form this as a subset. This set can also form Q as a subset. This set can also form R as a subset. This set can also form PQ as a subset. This set can also form PR as a subset. This set can also form QR as a subset. This set can also form PQR, like repeating itself, as a subset. And this set can also form an empty set as a subset. Now, whenever you take all these possible, these are the possible subsets that can come out from this set. Now, whenever you take all these possible subsets of this A and take them as one single set, that single set you form is called the power set of A. Now, the power set of A is written as this. So it is the set that contains all these possible subsets, which is P, Q, Q arrow, and so on. So the number of elements in the power set of A is given as 2 raised to power the cardinality of A. Now the number of elements here in this power set is actually 8. 1, 2, 3, 4, 5, 6, 7, 8. Now we want to test this formula now. What is the cardinality of A? It is 3. So we have 2 raised to power 3. 2 raised to power 3 is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So this proves that the number of elements in a power set is given as 2 raised to power the cardinality of that set. Let's give another example. Let's say A is a set of 2 elements, for example. What will be the power set of A? All the possible subsets that can be formed from here is 1, 2, 1 and 2. Then our empty set, 5. So there are 4 possible subsets you can form here. I want to verify this formula. What is the cardinality of A? It is 2 because there are 2 elements here. What is 2 raised to power 2? 4. So this shows that the number of elements in the power set of any set is given as 2 raised to power the cardinality of that set. So that's all for power sets. For power sets. Then the last one is proper subset. Proper stroke improper. Improper subset. So when we are talking about proper and improper subsets, we will still talk about the universal set. We will relate it to the universal set. Now let's say we have 2 subsets from a universal set. 2 subsets from a universal set. Let's say we have this first subset as P, Q, 1, 2. And the other subset as this P, 1, 2. Now all the elements that are in B are in A. Although these two are subsets of a certain universal set, probably we don't know, but they are subset of a certain universal set. Because even as they are subsets, B is inside A. We say that B is a proper subset of A because everything in B is completely inside A. So we say this B is a proper subset of A. Let me give an instance. If Africa was a subset, if Africa was the universal set, and Nigeria was a subset, and even Edo State is also a subset, or Delta State is also a subset. Now, because Delta State is inside Nigeria and both of them are subsets, we say that Delta State is a subset, is a proper subset of Nigeria, but both of them are actually subsets of the same universal set, which is Africa. So whenever you find a case like that, B becomes a proper subset of A. But if they had the same elements, let's add Q here. Now they now have exactly the same elements. Let's say probably the same number of people, or the same people in Delta State is the same people in Edo State. For example, I am here teaching in Delta State, and somebody exactly like me answering my name is also in Delta State teaching. Now, whenever you find situations like that, we say they are improper subsets of each other because they have exactly the same elements. But if everything in B is completely in A and not the other way around, we say B is a proper subset of A. So that will be all for this video. In our next video, we'll talk about some numbers. We'll talk about complex numbers, rational numbers, irrational numbers, integers, natural numbers, as well as every other number. So you get to know their symbols and how they are used interchangeably. So please, thanks for watching. Please do not forget, like and subscribe to our YouTube channel. Thanks for watching.